For this problem, we want to find all the rational zeros of x to the fourth minus 8x cubed plus 14x squared plus 8x minus 15. The first thing we should do here is apply Descartes' rule of signs. And Descartes' rule of signs says if you count all of the sign changes in your polynomial, then the number of positive factors will be that amount minus some even number. So let's start with that. We're going to also say that this is the function f of x to make this all work out nicely. So we're going to take f of x and count how many sign changes we have. We have 1 going from positive x to the fourth to negative x cubed, then 2. There is no sign change here, but there is one here. So that gives us 3 sign changes for the positive f of x. Now we're going to do the same thing with f of negative x. That'll tell us how many negative rational zeros there could be. So plugging in a negative in for every x, we get negative x to the fourth minus 8 times negative x to the third plus 14 times negative x squared plus 8 times negative x minus 15. That gives us positive x to the fourth. Here we have negative to the third power. That means there's 4 negatives. So again, that's positive 8x to the third. Just a quick note, this became positive because when we have an even number of negatives, 4 of them. And that's what we're doing for all of these. Again, here, negative x squared. That means that there are 2 negatives, it's positive again, so plus 14x squared. Then from here we have minus 8x, and then again we have minus 15. So counting the sign changes here, we have 1 sign change from this 14 to negative 8, and that's it. So for our positive rational zeros, we have from the f of x function 3 possible positive rational zeros. Or we could subtract 2 from this and get 1 positive rational zero. So there could be 3 of them, or there could be only 1. We cannot subtract 2 from this again, otherwise we would end up with negative 1. And there's no such thing as negative 1 rational zeros. So there will be exactly 3 or exactly 1. Now going to the negative rational zeros. In this case, we have 1 because it comes from the f of negative x. So the positive x gives you positive rational zeros, negative x gives you negative rational zeros. So because there was only 1 sign change, there is exactly 1 possible negative rational zero. We cannot subtract 2 from it because again that would leave us with a negative amount, which is impossible. So we know we will have exactly 1 negative rational zero. Okay, so going back to the original problem, we now need to check what the possible rational zeros are. And the way we do that is with the p over q method, or the q over p method, it doesn't matter which, so long as you just take your last number, your constant, so 15, and then your first number, which is 1 in front of that x to the fourth, and you're going to find all of their possible factors. So 15 has a factor of 1, 3, 5, and 15. These are the only numbers that divided evenly. 1 is only divisible by 1. So that was pretty easy. To find the possible rational zeros that could solve this problem, we take this number, the last constant in our original function. We take every one of its factors and put them over every one of the factors of the first number, which in this case is just 1. So we'll start with our first one. We have 1 and we'll put that over 1. Then we have 3 over 1. Then 5 over 1. And finally 15 over 1. These are our only possible choices. And each one of these could be positive or negative. So we put a plus or minus with each one. So our possible rational zeros, the list of them simplified is 1, 3, 5, and 15, all with a plus or minus attached. So we have 8 possibilities, and we know that we could either have 3 positive ones or 1 positive one, and we know that we will have exactly 1 negative one. So now we start our check. We will use synthetic division to check each one of these until we max out our possibilities. Meaning as soon as we find 1 negative one that answers the question, meaning we end up getting a 0 when we apply the factor theorem for our remainder. As soon as we get that 1 negative answer, we are done. We do not have to continue with the negatives. We can throw the rest out. And the same thing is true here. As soon as we get 3 of them, we can immediately stop. If we only end up getting 1 of them when we go through all of our choices, then it's perfectly okay as well. But we have to check them all until we get the 3. Okay, so going through this with synthetic division, we'll start with our smallest ones first. We have 1. We will perform synthetic division from this polynomial that we started with, the function. So remember, we take our constants out, 1, negative 8, 14, positive 8, and negative 15. We bring down our first number, which is 1, and now we're going to multiply by the outside number. 1 times 1 gives us 1. We add that to the number above. That gives us negative 7. And we repeat the process. Negative 7 times 1 is negative 7. Plus 14 is positive 7. Times 1 is just 7 again. Plus 8 is 15. Times 1 is 15 again. Plus negative 15 is 0. Since the remainder is a 0, that means the factor theorem applies, meaning x equals 1 is a factor. So this is one of our answers. We found one of our positive rational zeros. It's x equals 1. So we'll circle this for the end so we remember where it is. And in fact, we shouldn't really circle it. We'll just underline it to know to come back to it, as it's not one of our final answers as of yet. Now we'll go to negative 1. And the nice thing about this process is we do not have to start back at 1, negative 8, 14, 8, negative 15 from our original function. We can start off where we left off with the 1, negative 7, 7, and 15 just like above. As long as you get this factor theorem to apply where you have a remainder of 0, then you can pick up where you left off. If the remainder is not 0, then you do have to go back to this 1, negative 8, 14, 8, negative 15. Okay, so let's check if -1 works. We're going to bring down our first number, which is 1, multiply that by our -1, that gives us -1. Add it to -7, we have -8. Multiply that by -1, we get +8. Add that to the 7 above it, that's 15. Multiply that by -1, we get -15. Add the results together, we have 0. Again, we have a remainder of 0, which means this will also be one of our answers. And notice, because it's negative, and there is only one negative answer, we don't have to check the other negative numbers, meaning -3, -5, and -15 cannot be the solutions. So now all we have to check are the +3, +5, and +15. We'll start with the smallest ones, as those will be the easier ones to work with, and see if they work out. We now have 1, -8, and 15 that we're checking. Because the last one worked, we had a remainder of 0. So we bring down this 1, which gives us 1 times 3 is 3, plus -8 is -5, times this +3 is -15. Added to the +15 above it, we get 0. Again, a remainder of 0. So this is again one of our solutions. Now we just have 2 left to check. The 5 and 15, both positive. Right now we have 2 positive answers, but we must have 3 or 1, which means since we already have 2, we know we are guaranteed to get 1 more that will work. Now I can already tell from this solution right here, this quotient, that the answer is going to be 5. But I'm going to use 15 just to show you what happens if you pick the wrong value. So if we pick 15 and continue with our synthetic division, we have 1 and -5 now. Since the 3 worked, it was a factor. So we bring down our first number, which is 1. We multiply the 1 by 15, that gives us +15. Add that to the -5 above it, we get +10. This does not work because 0 is not the remainder we're looking for. So we eliminate 15 as a possibility, and we go back to the 5 that was left over. We do have to check it, as we could have made a mistake earlier, so we cannot just assume that it is a factor for sure. So we'll take our 5, and this is what I was noting earlier. We cannot use this quotient because the remainder was not 0. So we go back to the last time our remainder was 0, and we use the last quotient, 1 and -5. We bring down our 1, we get 5 times 1 is 5, add that to the -5, and we're left with 0. A remainder of 0 means it does work out, so we can give our list of solutions. All of the rational zeros that are answers to this problem are -1, +1, +3, and +5. These are all the values that we found using synthetic division worked with the factor theorem. They gave a remainder of 0.